Welcome back for lecture 12 on this series on Introduction to DFT. And today we are going to talk in this screencast about van der Waals interaction in DFT. We already discussed in the previous few lectures that van der Waals interactions are not easy to include in the exchange correlation functional in terms of the approximation. The issue being that it is a very much non-local effect, and all the local or semi-local functionals are not really good at that. So many developments have been made in trying to fix this issue, and I'm going to give you an overview of that in this screencast. So the references I use to prepare these lectures are shown here on this slide. There are a number of references out there. In fact, most of the development were made until the mid of 2010, so around 2015. Of course, there are still lots of development going on now, but the main families of corrections to include van der Waals in DFTs have been done over the past 25 years. So I need to give you a warning. Of course, there are many attempts to address van der Waals issues. I will just provide you an overview, and really the idea is that the person who is listening to this lecture will realize there are different possibilities to address van der Waals interactions. Some of them are not very computationally expensive. Actually, most of them are not computationally expensive, but they can be very important, especially in when you are interested in looking into biomaterial and interaction with biological systems, or if you have weakly bonded system like in 2D materials, for example. So it's a very active field. There've been a lot of progress recently, as I said a few minutes ago, and hopefully you will get an overview of this. I have to warn you that there is no such a thing as a complete understanding, or at least not a complete description that works all the time for including van der Waals interaction. That's also why we have this coexistence of different methods that are out there that you can try depending on your system. So van der Waals interaction were actually identified in 1873 by van der Waals. You see a picture on the right. So you know probably van der Waals as well in the context of thermodynamics with the van der Waals equation. So like an improvement over the independent dependent gas. So van der Waals did this as part of his thesis in 1873, and he later got the Nobel Prize in physics in 1910, I believe, for his various works to the field of physics. As I told you, it was discovered in 1873, but evolution led to animals to use van der Waals to their advantage. I showed you in the previous slide the gecko that's using van der Waals interaction as a mechanism for adherence to flat surfaces, of course. So you find van der Waals pretty much everywhere. You find them when you have interaction with surfaces, when you have biomaterials of matter. One thing that's important is van der Waals interactions exist in every single systems. That's something that's very important to realize. And of course, if you have van der Waals, that's just a component of the total force, if I should say, like if you have a strong covalent bond or a metallic bond or ionic bond, van der Waals interactions are much weaker. So even though van der Waals interactions are there as well, the relative importance is usually somewhat negligible, so that's not an issue. However, there are also materials where van der Waals force is the only forces are the only forces that are playing a role. So as I said, for example, in 2D materials, think about bilayer graphene, or think about biomaterials, or even noble gas atoms. In these cases, you do not have anything else than van der Waals, and therefore van der Waals becomes important. So van der Waals is a pure quantum phenomenon. Very often, people understand van der Waals as the interaction between dipoles, between instantaneous dipoles, and when classically you can find that the interaction from electrostatics of between two independent dipoles goes as 1 over R6. So this is kind of the, I would say, the average effect that actually works in most cases. So we want to look at the subtle observation of phenomena that happens because of van der Waals. Okay, so just I will remind you in a few couple of slides, but let's make sure we understand what van der Waals is. Well, in van der Waals interaction, what happens is that you have a density of charges, and you can have an instantaneous dipole that happens because you have a slight asymmetry that comes from the dissipation fluctuation theorem, uh, a slight asymmetry in the density, and it results to have a dipole. That dipole, for example, on the left-hand side on this picture, would then be felt, if you will, by the density on another atom, which will then have a response of its density moving and therefore creating another dipole. So this instantaneous dipole will actually generate another instantaneous dipole, and then the interaction between the two will be a van der Waals force. This is called the London dispersion force. And as you can see, the way I just described this to you, it's very much a non-local effect. In the local density approximation, or even the semi-local, what really matters is the density at a given point. That's the contribution. This is the kind of contributions that you have in the exchange correlation energy. Here, clearly, a local or even semi-local description will not encapsulate what I just described to you. So this is why van der Waals interactions are not easy to include in the exchange correlation functionals, as it is completely non-local effect. I'd like to have a quick note, very fast. The R minus 6 uh, dependence, so R being the distance between the two particles that we are looking at, this 1 over R6 dependence is actually an approximation of the London dispersion force. It's an excellent approximation. But for example, at larger distances, you have screening, so that interaction would be more like 1 over R7, for example. But at the same time, at the very long distances, that the force is even smaller. So the 1 over R6 is pretty good as an approximation. So I'm going to give you some terminology because we work with at the interdisciplinary between chemistry, physics, and biology. Usually in physical chemistry, we have kind of three types of weak forces. We have the interaction between permanent dipoles. That's a Keeson force. So those dipoles are there all the time, if we will. So this is not exactly what I just described. This is not the London force. You also have the interaction of the bi-type interaction, which is between a dipole that exists permanently and an induced dipole. So, for example, if you have argon, which does not have a dipole but could have an instantaneous one. So the instantaneous one, it's instantaneous dipole in argon, for example, um, uh, could emerge from the presence of a polar molecule like a HCl close to it. I mean, we understand this thing. This is a Debye force. The one we are interested in here really is the interaction between two instantaneously induced dipole, the one I just described to you in the previous slide. And this is really what we are interested in the condensed matter community. It has a totally non-classical origin. And this non-classical origin, of course, reminds you that the place that you have to work on is the exchange correlation energy. And you also realize when you think about this, when you think about what I just described to you, is that it's not easy necessarily to see how we could include that effect in a functional like the exchange correlation energy, which only depends on the density. Because you need more than one density to describe what's going on here, especially this idea of instantaneous dipole. Yet, according to the Hornberg and Kohn theorem, that interaction could be included in the exchange correlation energy. There is a place to do, but this is where basically um, your imagination has to play a role and say, we know it's there, we just don't know how to describe it. So we have a number of instances of that in science, of course, but the existence theorem, which is the Hornberg-Kohn theorem, the existence of this functional, tells you that it should be possible to describe it. It's just not easy to access that information. So here it's another picture of what I just told you a second ago. Let me say it again, just to make sure we all understand what a van der Waals force is before we actually try to describe it. You have two noble gas atom, neon, two atoms of neon, which of course are noble because they have the full shell, so they do not want to share electrons. So they are not going to do ionic bond. They are not going to do covalent bond, and certainly not metallic bond. They're just happy with their full octet on the external valence for the valence electrons. So they do interact by only one force, which would be the van der Waals force. And so you could have, and it would be the middle picture, an instantaneous dipole created by fluctuations in the density. I mean, the fluctuations that exist in nature no matter what, and even in the ground state. And then that instantaneous dipole will then trigger the presence of another dipole on the other atom, just because the dipole, if you will, is seen like an electric field on the other charge. So the charge on the second neon, so the B atom, will actually reorder to respond, if you will, to the dipole on the A neon. And then you end up in the final situation on the right, where you have two instantaneous dipoles that interact. And this is the van der Waals force. And of course, this is important in the case of neon, for instance, or krypton or helium, or those kinds of atoms, because this is the only kind of interaction that exists. So in DFT, it's not actually easy to introduce these van der Waals interaction. I just described that. And especially that they really come from these electronic correlations. Again, you could see the way I was describing van der Waals interactions about correlation between electrons. And so it is not easy to do. And again, according to Hornberg-Kohn theorem, this kind of quantum effect should be actually in the exchange correlation density. I mean, the exact one, which we don't know, of course, this is the quest. So this is not easy to introduce this in the exchange correlation functional, the exchange correlation energy functional. It is not easy to introduce using the density as your variable, which is, of course, what we need to do in the Hornberg-Kohn framework. So there have been different ways to fix this, and this is what I'm going to at least to address this, maybe not fix it, and this is what I'm going to talk to you about. So, so for the longest time, until 2000, I mean, people were already very happy that like GGA or B-trilip or PBE0, I mean, that kind of functional, semi-local, and also the hybrid function, people were happy that those functionals did an amazing job on covalent bond, on ionic bond, on metallic bond. So the fact that we were not able to address really the van der Waals interaction, even though it's totally absent in those approximations, was not too bad, because there was enough work, if you will, to use DFT on everything else. But yet we know LDA and GGA, and I said that a number of times in this course, and I hope it's clear now, LDA and GGA do not include van der Waals interactions at all. And of course, some people have been also a little bit misled, and I described that, and I'm going to say it again. If you take, for example, two layers of graphene and bring them together using LDA, you will find that there is a minimum of energy at 3.4 angstrom. Looks like van der Waals interactions are included, but in fact, it's a good result that comes for completely wrong reason. There is no van der Waals in LDA. Actually, if you do GGA, if you do the two layers of graphene and bring them together, there's the stable position is infinitely far away from each other. So this is what's happening, and so you need to really take into the account the van der Waals interaction there, and so the fact that it's a purely quantum mechanical effect makes it also harder, because that means that you really have to dig deep to know how you could include them in the exchange correlation functional, and the fact it's non-local by nature. So these are very difficult to get by DFT, very difficult. But people have come up with solutions to that. Okay. Um, so as I said, trying to fix van der Waals has been done by a number of groups, many of which I'm going to cite in just a few minutes, and especially in the past 25 years. And we are at a pretty good place right now, even though there is still room for improvement. And there are different kinds to do it. There are different ways to address this with different computational costs. So before I showed you the solution, I want to show you what the fluctuation dissipation theory tells you in terms of this long equation, which you should not worry too much about. It would be what you would calculate, at least in the first orders, um, to calculate to get that correlation, the fluctuation dissipation theory. So fluctuation, of course, we need this since we have fluctuation density. And you need to calculate that kind of term. I show it on purpose, not so much that you learn that equation, but mostly to show that it's not simple. And you have like W is the screen potential, alpha is polarization, you have dielectric response and that kind of thing. So it's complicated to do. It's a many body effect. Now you can approximate this pretty heavily and find a leading term, and then you end up with this 1 over R6. So this 1 over R6 term is really like an approximation to the right answer, if you will. So we know at least that 1 over R6 is justified. I mean, justified to use not just as an empirical result, but also as a good approximation. Okay. So now we can ask, why a lecture on van der Waals? Well, the lecture on van der Waals, I think I already motivated it, but I can do a little bit more. As we move further and the power and the accuracy of DFT has been established very, very clearly in solids and in molecules, people started to, of course, be interested in moving forward. I mean, you have different types of materials, like biological materials, biomaterials in general. And obviously, the field of biomaterials is so broad and so large, and there are so many applications and so much impact that can be done by understanding those materials on the computer. The people were interested in understanding van der Waals. So unfortunately, if you LDA is completely out of the picture for van der Waals interaction. GGA is not great, but GGA is great for many things. So people have mostly worked on trying to fix GGA to get the best of both worlds, essentially. So GGA for everything that it does well, and then van der Waals on top of it to fix one of its big shortcomings, which is, of course, the van der Waals interaction. So now you do have this kind of family of DFT, which is van der Waals DFT, and that becoming very important and actually pretty easy to use. And in fact, most codes that are freely available or commercially available do have a possibility to do van der Waals correction. But just as my motivation for this course was to really warn you that there are different ways to do it, and if you want to call yourself a DFT person, you can't just check a box saying include van der Waals. You have to know what you're doing. And so this is really the goal of the next 10 minutes of this presentation, 15 minutes of this presentation. Just to give you an additional idea of why van der Waals van der Waals forces are important. If you take a DNA molecules, for example, if you did not have van der Waals interaction, you would not have the helical structure of DNA, the famous structure that was highlighted by Watson and Crick. You would have actually a completely different kind of biomolecule that's shown on the bottom. And the life as we know it, I mean, literally, life as we know it would be a different story. I mean, it could even be impossible, certainly the one as we know it. So maybe something else would happen, but this is not something I can really comment on. So just let's go back to what we did. We discussed about this conventional DFT. As I said, sometimes PB does not include van der Waals, but sometimes for cancellation of errors, you see something that look good, at least for krypton. But if you look at on the right-hand side, which is like a pi-pi stacking, you see the PBE is pretty poor compared to the reference. And you would think B3 lip, which is really a non-local functional, which is essentially GGA with exact exchange, does not do a very good job at all in either case. It's not surprising because B3-lip does not really address the correlation effect. It addresses the exchange effect. And van der Waals interactions are really a correlation effect, not an exchange effect. So people have worked on this, and for example, you can look at this reference that I cite here, and came up even with this Jacob's ladder. You know, I introduced a Jacob's ladder from John Purdue for the exchange correlation functionals. Well, there is also a Jacob's ladder for the van der Waals interactions with different rungs, with hopefully an improving accuracy as we move up the ladder. The first rung, which I put in dotted lines, is not exactly the kind of things that we are going to talk too much about. I'll have one slide just for completeness. It's where you correct the pseudopotential. Then you have a number of techniques. For example, the first rung, which was important development, like really a correction to the energy. The rung two, a correction to the energy, but a little bit in a smarter way to find the coefficients. And finally, a rung three, we start to have density functional. So really addressing the density functional. So I'll discuss that, and I'll say a word about the rung four and above, like the RPA, the random phase approximation. So just a word about the rung zero. The DCACP, dispersion corrected atom center potential. Here, the idea is really to correct the potentials to the pseudo potential to try to encapsulate some of the effect of the van der Waals. So this is not something that we use a lot in the material science code. I mean, this is not something you use, for example, in VASP or Abinit or Quantum Espresso. But this is something that at least if you hear about this, this is really the lowest level approach to trying to solve this. But I'd like to spend more time on the first rung. The first rung, it's actually an interesting effect because the first rung is saying, all right, I am missing an important piece of the energy here, and as a result of the forces. And that thing that I'm missing really is this 1 over R6. And so each atoms by pair interact through van der Waals interaction with a 1 over R6 interaction. So the first thing you could think is, well, why not add that correction to the total energy since we know it exists? We don't have it. We do not treat it quantum mechanically at all. It's really treated a purely classical way. I mean, the 1 over R6 has a quantum mechanical origin, but the way it's treated is kind of empirical, if you want, because it's added just after the quantum mechanical effect is done. And so it's empirical in the sense that the coefficient C6 that you need between every pairs of atom is an empirical coefficient that is actually used to try to reproduce the experimental data. So it is not truly addressing the issue of the exchange correlation functional. Actually, we do not change the exchange correlation functional, and typically this is done on top of PBE or on top of BLIP or that kind of things. It is really correcting the total energy. So people did that, and there were a number of improvement over that. For example, this work where the C6 was actually damped. So in other words, you have this function f that depends on the distance between the atom, and you can actually add something to it to avoid this catastrophic attraction at very low distance. That catastrophic attractions in the dashed line does not exist, of course, in reality, because when the particle would get so small, you would have a very strong force coming from due to the Pauli exclusion principle, because the Pauli exclusion principle does not allow atoms to get very, very close to each other, because they would then occupy the same state. So this is interesting. So this is the kind of dispersion that you have. That's very interesting. One very well-known one is called DFT plus D2. This is extremely well-known. This is a very popular way to approach. And it was introduced by Grimmie in 2006. And in this case, the coefficient C6 were obtained no longer exactly not no longer during empirical approaches, but as the result that you have here. So a C6 between a pair of atoms I and J would be obtained from the geometrical average, so the square root of the product of the C6 of the individual atoms, and those C6 of the individual atom would actually be obtained from intrinsic properties of the atom. For example, the ionization potential, I, and the static polarizability, alpha, and N being the number of electrons. So at least here we have something a little bit cleaner in a sense that it's not problem dependent. It is intrinsic properties, so you no longer have adjustable parameters. So it's doing a good job, but as you would expect, it's not exact, it's not perfect, but it's a very good approximation. So that was DFT plus D2 is whether a drug, still a drug one. Now, as I said, it's not perfect because those C6 is completely agnostic about understanding what's going on around with the density. I mean, how does that affect the fact that you have an atom in a certain environment? It's completely ignored here. It's because it's using the intrinsic properties of the atom. So there were improvements on that. In fact, the same group from Grimy in 2010 came up with the next version of, so instead of DFT D2, it was DFT D3. And now the C6 coefficients are now obtained by depending on the environment, and the environment being the hybridization state of the atom. So the fact that an atom, for example, to take an example, if you have an atom, a carbon atom, which is in sp3 hybridization, like in diamond, it would have a different C6 than if you have a carbon atom in an sp2 hybridization, like in graphene, for example. Other people have tried something similar but different in the sense that including the environment, like the Tkachenko and Scheffler, so very well known as DFT-TS for Tkachenko and Scheffler. In that case, the idea was to use the partitioning of the molecular electron density, again, to take into account the environment effect. So these are very popular methods that are available in most codes. And so far, none of these methods really are doing anything on the exchange correlation functional. They are correction to the total energy. And they do work very well because that correction to the total energy also influences the relaxation of your system, right? Because you're trying to minimize the energy. So you are trying to basically make sure that the van der Waals interaction is included in the calculation of the relaxation of those geometries. So these are really good methods. Actually, these methods are not very expensive computationally speaking compared to, let's say, using a Kohn-Sham calculation. These are actually very inexpensive, typically done on top of PBE. Okay. So there were people also interested in trying to improve, go to the next rung, and in this case, actually try to address the correlation functional, so the exchange correlation energy functional, trying to make it non-local, to include effects specifically for van der Waals interaction. So these are two examples here with the two that I give in the two references. And the idea there really is to try to come up with methods to include those effects directly into the quantum mechanical picture. So from a fundamental perspective, this is quite attractive to try to do this. It's more computationally demanding, but it seems to be more staying into the spirit of staying within DFT. I am not saying that they are necessarily superior than to the D3 or the Tkachenko-Scheffler. Not necessarily. It's just a different perspective and maybe a path towards to have something universal, which we have not achieved yet. So I'm going to give you some example here. So it's easy to remember what is what, because VDWDF means density functional. So you're changing density functional. They have a number of groups like Landgraf and Lundqvist. There also another group like Klimes and Michailidis and so on and so forth, and with some reference here. So name that you may hear in the literature would be DF, DF2, and then there's a number of names, and I know they are available directly in places like GPO or VASP, but also other codes like OPT, 88B, that kind of thing. So all those things are now can be obtained and can be used in most codes. Now, which one should you use? Well, the thing is that from all the ones that I described to you so far, some of them are good in some instances, some others are better in other instances. There is no rule really. But it's good to know that they don't exist. And if you are doing a long project and you are going to use van der Waals interaction in your project, it's probably good to do some benchmarking to know which one is best for your purpose. So here's an example again from that paper showing the different type of correlation. This is a complicated table. I mean, frankly, I'm not going to spend too much time on it. It's mostly to show you a little bit where we are standing now with the different methods. So you can have a very long list. This is actually a reduced list compared to what's available. But you can now understand DF, DF2. You have others that I mentioned in the previous screencast, the RVV10. You remember RVV10 being added to scan in the paper from John Purdue. So there are different methods that you can use with different cost, computational cost, and different accuracy. One thing that is probably good mentioning is that the computational cost I mean, the accuracy does not necessarily always increase with the computational cost. So this is again something that you have to consider. And usually what people do in the different techniques, the different approaches, is to look at things that are more or less repulsive as a function of distance. So this is a typical plot that you would see again without going into the detail, but the different approximation will have different behavior, a different asymptotic behavior, for instance. So that's interesting. Now I have to tell you a little bit about the rung 4, very little about this, which is perturbation theory. So the perturbation theory would be to try to treat the correction to van der Waals as a perturbation theory, basically solving the long equation I showed you before. And would be done in different level of approximation using a Feynman diagram and using different diagrams of higher and higher complexity, and would be done within the framework of the RPA, so the random phase approximation. And it allows to include the screen non-local exchange, the long-term dynamic effect, I mean, in the screen potential, and that would allow to get some van der Waals bonding included. RPA is extremely expensive compared to everything I mentioned to you before. This is done mostly by people who are trying to find benchmarks to develop other techniques, other methods for van der Waals. But I think it's good to know that it exists. And if you will, the RPA is really about going back into the quantum mechanical problem. And the equation I was showing you earlier can be written as a series of diagrams, as shown in the box on the right hand side, where you are the full interaction can be obtained by a series of interaction using Green's function, right? This is obviously not a course on Feynman diagrams, but the Feynman diagrams can be actually expressed as those Green's function between fully interacting the full line and then the non-interacting Green's function with different levels. So using this the Wick diagrams and Wick description. So that's the idea in RPA, was to add more and more terms into the perturbation theory to try to actually capture the effect of those fluctuation-dissipation theorem and to actually calculate this from first principle. So before I wrap up this screencast, I would like to show you some examples. There are plenty of examples in the literature. I just picked a couple here that are kind of benchmarking. Here, it's an example of the methane, a solid methane, so a molecular solid. Of course, the methane are not going to interact between each other using no strong bonds like covalent, ionic, or metallic. Therefore, the driving force for the solid, for the molecular solid, as usual, the driving force, van der Waals interaction. So this is a good example to test the importance of van der Waals interaction. So if you look at the left-hand side and you look at the red vertical line, which is the experimental data, so it's what you want to obtain, you can see the different methods. As we know, PBE grossly underbind. PW91 is another GGA method. And so they do underbind, they do not actually include van der Waals at all, but because they make errors in the rest, it still finds it still finds an interaction energy between the molecules, but it's not of van der Waals origin, it's just of errors in the fact that they're semi-local semi-local functional. Now you can actually correct those functionals, both the non-local one, the semi-local one like PBE, or the non-local one like B3LIP and PBE0, which are both hybrid functionals, as we discussed. And here they've been corrected with the Tkachenko-Scheffler or by the Grimy method that I discussed. You remember the rung number two. So those environment-dependent C6. And you see they're doing a pretty good job. I mean, certainly PBE Grimy, which is a very popular one, and also PBTS are doing a fantastic job, I would say, to get the right absorption energy and the lattice constant. You can check the table on the right. I like to say just one more thing is LDA. Again, LDA is a local functional, so there is absolutely no hope it can capture van der Waals. But look, LDA doesn't do a good job at all, a bad job at all. He's doing a pretty good job, I would say. But this is totally fake. This is totally an illusion because LDA does not include any van der Waals, but because it overbinds, it includes interaction within the methane molecule that makes it look like it's doing a good job, but it's only doing a good job because of all the constellation of errors. So I really like this example in this paper because it really it allows me to wrap up a lot of things that I've said in this course. I always hesitate to show the next slide, but I'm going to because this is a typical slide you see when people try to look at comparing the different methods. I'm not going to too much detail here because it's a little bit too much between the interaction between argon, so an argon dimer and a krypton dimer, and if you want to know more, you can pause the screencast and look at this. But the take-home message is this one: is that you have different type of functionals, some being corrected for van der Waals, some not, like the LD and PB are not corrected for van der Waals. And you see those different approaches. They're doing a pretty good job at finding like the lattice constant, but they are not on top of each other, right? These are different approximations. And it's not easy to know which one is better than the other one unless you compare to experiment. But again, there could be other reason why maybe you capture van der Waals pretty good, but because you don't capture the rest, maybe it doesn't look so good. So you see what I mean? So you have to do this kind of benchmarking, and these are kind of benchmarking that we see a lot in the literature. And I hope you understand now some of the jargon that's on the right. Okay. And as a final example, I want to show you the case of a molecule, again, a molecule that's not going to interact through ionic bond, metallic or covalent bond, and on the surface, like a copper 111. This is very, very typical to look at a molecule interacting on a 111 surface of an FCC metal. So this is an example here of hydrogen. This is a paper from Lee in the Journal of Physics Condensed Matter. And the plot on the right is maybe a little bit more readable than what I showed on the previous slide. And you see, so ref PBE is another type of PBE. So and ref PBE and PBE, again, do a pretty poor job, especially far from experiment. However, if you add some van der Waals interaction like DF and DF2, so the red and the yellow curves, they get much closer to experiment. They're a bit deeper. The well is a bit deeper, but at least the separation length is closer to the experiment. You can see that the other methods like D3 and so the Grimy approach or the Tkachenko Scheffler, they do a good job at correcting the PBE results. So they obtain, there is in fact indeed a minimum in the curve, so including the van der Waals, but here it's too strong. So this is a particular case. So you see, the point is, it depends on the accuracy you want. It depends on how fast you want to do them. But those methods for van der Waals corrections do exist. They are not perfect, but for a class of system, you have to make sure you make that study when you start your calculations to make sure that you're actually using something that's going to give you something sensible. Because if you end up reaching conclusion on your results that you did not benchmark, this is a recipe for disaster, and it's a recipe for have a paper that's well cited for saying because it's wrong. So we always say that it's okay to be well cited when we are wrong. It may be okay, but leave that to others. Don't be that person or that group. I'd like to thank you very much for staying all the way to the end of this lecture. I hope you understood a little bit about how we treat van der Waals interactions in DFT, and I thank you for your attention. And if you have any questions, as always, you can put them in the comments in the comments of the YouTube channel. Thank you very much.